I'll go back to a problem that I sometimes assign for homework, and this year I didn't. I said, I'm just going to do it in class. So again, this was this is chapter 2, right? This was section 2.3, number 48. And we started to do this last time, so let me cover up this. Here's what we were given. We were given that we had a set of linearly independent vectors, whatever that means. And then we were given another vector. V is a linear combination of those vectors. And so what you're supposed to prove in problem 48, it's a longer one. I don't want to write the whole thing out. You can look in the book at the statement. But you're supposed to prove that, if you look at the bottom here, I wrote it, this set in blue is linearly independent. Now, what set? Do you see the difference? The difference was I took away one vector, v1, and I replaced it with v. Now, what do we know about v? V is some linear combination of all those. I think there's one more thing we know too. I think we know that we are also given, I think they told me that C1 does not equal what? 0. And actually you need that here, or else you'll see the proof will kind of fail. We're going to use that at some point. All right. You guys with me on what I did so far? Not much, right? What are we going to do next? Unpack. Let's go with the statement first. What does it mean for vectors to be linearly independent? I wrote it down here. I said if you have this equation, dv plus d2v2 up to dkvk equals 0, that only has the solution. Oh, remember what we called that kind of solution? Yeah, it's called the trivial solution. So let me write that down. It only has the trivial solution. That's what it means to be linearly independent.
Is the first EV, is that considered E1, V1, or is that just?
So okay, let me make a point of this, because that's interesting. Up above, I wrote down what it means for V1 to Vk to be linearly independent. But the reason that I used a V here is because we're trying to prove that if you take the set and get rid of the V1, right? We get rid of that and put V in there, it'll still be linearly independent. That's what we're trying to prove. Do you understand what we're trying to prove? That's why down here, I didn't put V1, I put V. But up here, when I was saying what we're given that if we have V1 there, then all those constants have to be 0. Do you understand? And one other thing that I did that I think is important to understand, because when I unpacked this, originally I had C's here. But then I took them away and replaced them with D's, because I had already used the C's up here, right? And there's no reason that these constants have to be the same as those constants. They just have to be constants. So I used a different letter. But it is true that the vectors have to be the same, except for one vector is different. What's the one vector that's different? Yeah, we put a V instead of V1. That's what's different. Are you guys with me so far? All right. And by the way, this problem is significantly more difficult, in my opinion, than the proof that we did last night for homework. It's one of the reasons I don't assign it anymore. It's a great problem, but I think it's more difficult. Because now you have to figure out, like, how do we show this equation only has that solution? And the answer is, well, we have to use our given information. We unpacked this. We know that this equation only has one solution. Actually, they're very similar looking, aren't they? really the only difference is that this one has a V1 and that one has a V. Now we have another equation, right? The other equation we have is right here. We're going to use that. And what I'd like to do is I would like to substitute in this equation for what? What is it I want to replace? Yeah. I guess all the C's have to become D's, but whatever. But more importantly, what's the big difference between the two equations, that the one that we're given and the one we're trying to prove?
One one's equal to 0,
Mm-hmm.
the other one just says equal to V.
Oh, yeah. This one has equals 0. So the red one, or the brown one, is more like the brown one down here, I would say, because both of those equal 0. This one just tells you something about V. But what I'd like to do, guys, and see if this makes sense, see that V1? I'd say that's my target right here. I don't want it to say V1, I want it to say what? V. And so what I'm going to do is I'm going to do something you did back in like high school algebra. You did substitution. I'm going to replace that V1. With what? Well, I'm going to bring this equation down, and I'm going to try and get V1 by itself. Can I do that? Well, I think we can write C1V1, which is the right-hand side, is actually equal to V. And then I'm going to move all this stuff to the side with V. So it'd be V minus C2V2 minus C3V3 minus all the way up to what would be the last thing you subtract? CKVK. Does that make sense? Okay, then what? I want to get V1 by itself. So what does V1 equal? Yes, we're going to divide by C1. And by the way, now you might understand why it was so important that C1 is not 0. Because you can't divide by 0, right? So that's interesting. So let me try this. I guess it would be V1 is equal to 1 over C1 times V. And does that make sense? Yeah, that makes sense because these are constants. Remember, you can't divide matrices, but you can divide numbers. Minus C2 over C1 V2 minus, well, dot, 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 minus the last one would be CK over C1 VK. So that's what V1 equals. Are you with me? Mitchell, what do you think? Okay, good. So here's what I do now. Remember I said this is my target here? This thing right here? I have V1 by itself here. I'm going to substitute it into the Brown equation. So, we know that C1 times all that green stuff, because that's what V1 is, plus C2V2 plus dot 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 plus CKVK equals 0 has only the trivial solution. Are you with me? By the way, what is that goes in there? I better write that out. It's 1 over C1 times V minus C2 over C1 times V2 minus dot 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 minus.
I thought you backed it out with C1 when you were
Yeah, so I'm trying to use the different colors to try and explain what's happening here. Let me see if I can explain it with those colors. The green equation is this one with the V, and it doesn't have a 0 anywhere, right? So where did I do some factoring? I divided everything by C1, and I got V1 by itself. And the reason I did that was, in the brown equation, where it used to say V1, I now put all that green stuff. Is that okay?
Which one's the brown equation?
The brown equation was this. Almost be better if they were next to each other. You with me or no, Zach? Take that brown equation. Here's the 0 vector, just like it had. Here's VK, just like it had. Here's V2, just like it had. The only thing different is, instead of V1, now, since I isolated V1 in the green equation,
Okay, I got it.
now you got that?
Yeah.
Cool. That's good, guys. So what I know is that this crazy thing only has the trivial solution. But let me rewrite this. First of all, what do you notice is going to happen over here? This C1 is going to cancel with every one of those C1s. You see that? So it actually really simplifies nicely. Let me write down what the new equation becomes. I think I'll write it in black because, I mean, it's still the brown equation, I guess, but since the C1s cancel, the very first thing you're going to get is V. Right? Now, then the next thing, you're not going to get a V1, you're going to get a coefficient of V2. And I claim that the coefficient of V2, let me write it here, will be C2, which was the brown number, minus C2 over C1. Because you're going to have, there's some V2s here, and there's also some V2s in there. Oh, wait, not minus C1. Wait a minute. Right. So I guess, yeah, instead of going through this, right, here's what I'll say next. I'll say, notice, let's just focus on D2. D2 has to equal what? C2 minus, well, again, the brown C1 times the fraction in green, C2 over C1. And then what you guys said, right? The C1s cancel, and then the C2s subtract, and so D2 equals 0. Right? We just proved D2 equals 0. You guys with me? And then I'm going to say, similarly, D3 equals 0, dot, dot, dot. You could do the same argument. You would get DK equals 0. Well, if all those equal 0, then what we're down to is this equation. We're down to D times V equals 0. But that implies that D equals 0. And that implies the only solution is the trivial one, and that proves that the vectors are linearly independent. That was pretty complicated. You had to go term by term and prove that each one of them was 0. But it all comes from starting with what you're trying to prove, unpacking it, looking at your given, unpacking it. We did some algebra, and we got it to work. And that was the toughest proof they had in that section, the last problem of that section. So if you understand that, I think we're making some progress, which is pretty cool. All right. We're at 11 o'clock. I think we should stop for now.